First, as part of our programming for Space Week, step aboard the deep spacecraft known as Voyager.
The road to the stars begins at the foot of the San Gabriel Mountains in Pasadena, California. Caltech's Jet Propulsion Laboratory is the nerve center of NASA's planetary exploration program. Here, Earth got the first close-up look at its nearest neighbors. Beginning in the 1960s, a generation of probes called Mariner took us to Mercury, Venus, and Mars. By the end of the 1970s, time had come to explore the outer planets.
Goldstone, I would just like to confirm you have acquisition of Voyager signal.
That's affirmative at 1649.15. We have receivers in lock.
Earlier, two Caltech students working at JPL, Michael Minovich and Gary Flandreau, saw a rare opportunity. For the first time in 2 centuries, the outer planets would be aligned on the same side of the Sun. A single spacecraft could encounter Jupiter, go on to Saturn, rendezvous with Uranus, and finally reach Neptune. The mission was nicknamed the Grand Tour. But the American Congress would not approve the budget, so JPL proposed a compromise known as Voyager. 2 spacecraft, Voyager 1 and a backup Voyager 2, would go to Jupiter and Saturn. Uranus and Neptune would become an option. Caltech professor Edward Stone would lead the scientific team.
We were indeed fortunate that our technology was ready, because this grand tour, this alignment, occurs only once every 176 years. And if it had occurred 10 years earlier, we probably would not have been ready to have taken advantage of that opportunity.
For a spacecraft, a planet can act like a natural fueling station in space. The 2 Voyagers will depart each on a slightly different course. As they approach Jupiter, their speed will increase as the planet's gravity hurls them around like a catapult towards Saturn. There, Voyager 1 will fly by Saturn's moon, Titan, and then leave the planets. If Voyager 2 receives the go-ahead, it will continue on to Uranus. Flying by Uranus will boost its speed by nearly 5,000 miles an hour and alter its course for Neptune. The accuracy required to reach this remote planet has been compared to a golfer sinking a putt 1,000 miles away. With exacting skill, it will be the closest journey of the mission. The journey to Neptune from Earth would normally take 30 years. Aided by gravity, Voyager will make it in 12. Voyager's first project manager, Bud Schurmeyer, was chosen to make it happen. Now retired and an avid glider pilot in his spare time, he is a veteran of the early days. In the 1960s, Schurmeyer directed the Ranger probes that put America into the race to reach the moon. Later, he guided Mariner 6 and 7 to Mars. Until then, the importance of photography in planetary exploration was uncertain. But the role of cameras on future spacecraft was assured by powerful images from Mars and the Moon. For Bud Schurmeyer, Voyager was an even greater challenge.
The decision as to what experiments would fly and what scientists would be principal investigators on the mission involved a very time-consuming and long and sophisticated process. The first chore was to pick the team members. The key team members at that time consisted of the spacecraft system manager, when I selected Ray Heacock, who I had worked with in Ranger and Mariners and knew very well.
Heacock would develop the most intelligent spacecraft yet built. Voyager could virtually fly the mission by itself, although its 3 onboard computers were less powerful than today's.
Any good, PC today is going to have several 100,000 words of memory, and no one would think of buying a computer with the limited capabilities that the Voyager systems have. And of course, today, no one is thinking of building for spaceflight computers of such limited capability. But the thing that these computers had was reliability. And being programmable through ground operations, we can still have it perform very complex and sophisticated operations.
11 science instruments on board Voyager will survey the planets. They will detect particles and magnetic fields. They will probe rings and atmospheres, measure their temperatures and wind speed, and determine chemical composition. The remote sensors and high-resolution cameras are mounted on a fully movable scan platform. Voyager was also designed to withstand the rigors of deep space and of launch. Cape Canaveral, Florida, August the 20th, 1977. Mission design manager Charles Colhayes remembers.
We launched Voyager 2 first, and it got underway okay. And then several days later, in early September, we launched Voyager 1. Well, when we launched Voyager 1, and this huge Titan Centaur rocket left the launch pad, what happens is the Titan, the solid rockets thrust for a while, and then the center liquid stage thrust, and it gives the Centaur all the speed it can. The Centaur then goes into a circular orbit around the Earth. It fires its engines, and we finally get underway. Well, while we were all at the Cape, we noticed that the Centaur had used 1,200 more pounds of propellant to get into this coasting orbit than it should have used. And we realized there had been a malfunction in the Titan burn. Basically, the fuel and oxidizer had not mixed at quite the right ratio. And when it finished its job, it had not given the Centaur enough speed. Now the question was, does the Centaur have enough fuel left to fire up again and get us underway for Jupiter?
If not, the spacecraft will lack the speed to catch the trajectory to Jupiter. The dream of the Grand Tour hangs in the balance.
The bottom line on that is it made it, but it only had 3.5 seconds of fuel left in the tanks. It did have a normal guidance shutdown. 3.5 seconds later, the tanks would have been empty.
The troubled launch is an omen of things to come.